So over the last few years, I've been thinking a lot about and automating, thinking about providing decision support, automating, upskilling people who work in the development function. And I've spent a fair amount of time getting deep in the whole AI picture. I can actually program in TensorFlow now. So I've had some time for some hands-on experience. And what I would love to do in this talk is sort of give you my total overview of the big picture of AI and where we are in terms of its evolution, why it's taking off, why this isn't just another hype thing. That's because of the economics. And then I'm going to, because this is an Aptage presentation, I'm going to position Aptage in that space. Hope you'll indulge me in that. Again, I'm going to say things, I hope not everyone's going to agree with what I say. That'll give us an opportunity for questions. One of the impressions that I hope to leave is we are still, in spite of all the hype, hype is probably the wrong word, in spite of all the media attention and clearly economic success of the state of AI, it's still very much early days. And so there's a whole lot to be learned, discovered, discussed, and whatever. And engaging that discussion is one of the fun parts of life right now. So let's talk about some precursors. I don't know, I was surprised to learn that neural nets were actually, the first computational neural nets date back from the late 40s, early 50s. And the concept, why they did this was to actually simulate brains and simulate neural processes. Those who remember some of the early writings of Papert and the other guy, the MIT guys, what they wrote back in the late 50s was that this is an interesting idea, probably won't ever work. It's too computationally intensive, but a good thought. And then they went into thinking more about inference engines. What happened was there was sort of two breakthroughs that made this practical. One was this so-called backpropagation algorithm, which is used for updating neural nets. And the other is just having all these GPU units and the cloud which deploy them so that we essentially have enough compute power at our hands and we have an algorithm. By the way, the backpropagation algorithm, for those who remember their calculus, is just the chain rule. But someone figured out how to make that practical and be able to handle very large neural nets. So we see now what neural nets do is they just model neurons that are interconnected with each other. And then what neural net training does is it trains the weights between them. Now, if there's more specialization, then you have types of neurons, you use convolution filters for that. And as we'll talk a little bit, more sophisticated neural nets act like real neurons in that they tend to be more Bayesian than deterministic. Or Bayesian, then yeah, let's just leave it at that. So also about the same time, people were building inference engines that's led into things like expert systems. And what you do there is you develop a lot of rules and then you tell it how to apply the data it's getting with the rules, and it gives you an answer. There were some early interesting successes with inference engines, like there were things that could actually prove theorems with this and whatever. But it certainly has lost out as the primary thing to neural nets. However, it's really the combination of the two that has made AI really successful today. And then, as we're going to discuss as well, the predictive analytics is certainly a precursor to that, and particularly the resurgence of Bayesian thinking. Almost everything in AI is Bayesian-based these days. So, whoops, wrong way. So what happened is we really looked at the intersections of these things, which is modern AI. Modern AI technically is a set of techniques that get applied in an ad hoc way to whatever problem they're on. So if you look at the combination of inference engines and Bayesian predictive methods, this is the alchemy system that's put out by Professor Domingo at Washington University. the combination of computational neuroscience and, again, some amount of inference engines. You look at what happens there. They have some innate rules that they use to sort of get to design the neural nets, and then the neural nets get trained in all kinds of ways, either trains itself or is trained by others. But what we're learning is that human intelligence and artificial intelligence, at the very basis, are derive their understanding of the world by making predictions based on the input and innate rules. So natural language processing, you hear some sound waves, your system predicts what it is those sound waves might be. That's what you hear, but you might be wrong. And there's all kinds, the study of illusions, visual illusions, and audible illusions are based on this thought. Self-driving cars, what do? They look at all the input from all their sensors, and they predict whether they should take action or not, whether there'll be an accident, and then if so, they'll take action. However, this came out on The Verge a couple of days ago. Uber discovered why its test cars killed someone. And what happened is essentially their Bayesian model wasn't good enough to prevent this from happening. It wasn't that the sensors weren't working. It wasn't that the code didn't work as designed. It was essentially a problem in Bayesian learning. Which brings us to a question we'll talk about quick in a while how would we know if a Bayesian algorithm was good enough to deploy? Okay, so moving this forward, I want to talk about the thing is that AI is not there are really flavors or levels or kinds of AI. And people just talk about AI in general, but looking at this more deeply, it really is helpful to partition things into these three categories. I just, again, this is not mine, this is just good thinking in the field. And narrow AI is, I think, a really good term. It does one thing really well. And this is where we've had the most success. And so if you look at AlphaGo, which is sort of made history by being able to play Go when the early philosophers said, you can't play chess. A machine will never play chess very well. Then it did, and they said, well, that was brute force. You can't use brute force to play Go because it's combinatorically too big. So then a Google subsidiary, AlphaGo, actually, the Google subsidiary built a thing called AlphaGo, which they just, with a very deep neural net, and they trained it against a whole lot of games and included a bunch of inferences to get it started. And it beat the best Go player in the world. And it made some moves that no one ever saw coming, that people still write about. How did it know to do this? No one told it to do this. It just figured it out on its own through this neural net. And that scared a lot of people because it means that we're making some progress. But we don't know why. We don't know why it figured out how to do that. We just know that if we build a strong enough simulation of how a Go player would think, it trained itself that it predicted that would be a good move. And then what happened, it was on the 5th rank for those who know Go. And then 30 moves down the line, it turned out to be the critical move that won the game. And it probably plays better than any Go player in history of the game. So that's huge success. The other thing that's happening right now is sort of the democratization of narrow AI, where we have the Kaggle website with lots of data, which is open source, lots of data sets to play with and challenges and the like. And then we have the TensorFlow Learn environment that Google has, where they made their TensorFlow neural net and other software available. It's easily accessed through Python, and they have lots of lessons now training people how to use this. And that, of course, the reason for that is we need a lot of people who can know how. This is sort of the next generation for what our coders are going to do. Wide AI is things that are just supposed to be, or sometimes known as AGI, artificial general intelligence. And these are things like Alexa, Siri, Google Assistant, whatever. And it's supposed to do what you ask it to do.
I don't know that one.
That was my friend. I always should be careful saying Alexa in this talk. Then there's conscious machines, excuse me, which are supposed to actually think, be intentional, you're supposed to anticipate your needs rather than just respond, just do what's asked. There's a whole lot of philosophical debate about whether this is ever going to happen or not. My favorite, people take positions, my favorite position is reductionism. I have a reference to the end of the presentation. And I'm working from the bottom up on this chart. What is the state of the art? Well, there are people who say it's impossible, but philosophers have been saying various kinds of intelligence are impossible for a long time. And our history as a good Bayesian, the evidence is the philosophers are always wrong in these predictions, period. And they'll be wrong again, because there's no laws of physics that are broken with a conscious machine. In fact, we all sort of know biologically how to create these things. I have a very bright 3-year-old grandson. On the other hand, there's some really interesting, whether it's just going to be a very much bigger, elaborate neural net. The neural nets we build are minuscule compared to the neural net of the brain. And some people are suggesting that the brain and the neural nets and conscious machines may take quantum computing. Then there's some people who claim that'll never be done in silicon, but it requires carbon. And this is all good discussion, but the point is it will happen. The question is how and how soon, because no laws of physics are broken by having conscious machines. That said, I wouldn't worry about it for a while. My view on the wide AI, and there's a whole lot of literature on traffic on this on the web, is the wide AA stuff, Alexa, Siri, whatever, it's sort of like early days of cell technology. It doesn't work anywhere near as well as we would hope, but it works better than we would ever expect. And it's enough to generate a big competition now between Alexa, Siri, Google Assistant, Cortina, and the like. I believe you can hear this. So Alexa, are you better at AI than Siri? Alexa, she's ignoring me. Are you better at AI than Siri?
Sorry, I'm not sure about that.
Yeah, I get that answer. Did you all hear that? I get that answer a lot. So, on the other hand, the narrow AI, as I said, the AlphaGo example, it's a whole lot better than we expect. And because of the technologies and the readily available TensorFlow and other kinds of AI frameworks that work in computational frameworks that work in Python and the cloud computing, it really has turned a corner in practicality. And that's, we're going to focus a little bit more on that thought coming up. So this is really important, though, for those of us who care about the future of AI. We don't know why these algorithms work, why some work and some don't. If you actually are building a practical AI solution, it's much more trial and error and intuitions about how convergence rate should go, the landscape, the penalty function landscapes, and that sort of thing. It uses a lot of really sort of practical math that we all learned in advanced analytics and probability courses in probability theory and the like. But it's sort of an ad hoc application of those ideas. We don't really know. So here's a quote from a major researcher at Google, who of course would know, because they use a lot of the narrow AI for a lot of what they do. And as I say, they don't know why they can't predict in advance which algorithm is more likely to work, will likely work and won't, and which ones won't. Now, the other thing is interesting is that people for a while have talked about sort of the maturity models for analytics, and there's a variety of these in the environment right now. If you go on Google and ask for analytics maturity models, you'll see several flavors. Here's one. They all sort of start at the beginning. This is the descriptive analytics, is what is the stuff you learned in your stat classes. It's good for monitoring what has happened, and for things like operations management and the like, controllable processes, Deming stuff. And that's pretty mature. I mean, we really know that stuff. In the analysis of variation and whatever. If you go to the next level, though, people started looking at predictive methods. A lot of predictive methods are just curve fitting and the like. But we've seen a resurgence of predictive methods in the end are building probability distributions and interacting and looking at manipulating probability distributions put you right in the middle of Bayesian thinking. And so what there has been is a resurgence of Bayesian thinking in the predictive area. This is really important. Now, prescriptive analytics, and there are people who have other flavors of this, makes good enough predictions that at least can recommend actions. And so what the next step is, okay, we got a probability distribution. We're going to interpret that with some sort of rules engine to figure out how to prescribe things. And now what you see is happening is the analytics and AI is sort of converging already at this level. And so this has just been another thread in history that has led to the current AI. And now we're taking it one more level where we have autonomous and essentially autonomous analytics with like the car, which is not only recommends actions, but takes actions. And we have those too. And some of them are good enough now to deploy and some of them aren't. We're gonna need one more thing though. And this is what I'm talking about, the future of analytics. As I said, the guys who are building AI solutions don't know how to measure the quality of their solutions in a way. So if this really were a science, we would have some sort of measure for determining when one AI solution is better than another. And not only in the narrow, we don't even have that in the narrow case, let alone the wider general cases. Now, I don't think that's a huge surprise because we don't know how to measure human intelligence very well either. And one of the things that's interesting, I think, what we're going to see, this is me being very futuristic, is we're going to learn a lot more about human intelligence as we start building wider artificial intelligence and approach conscious machines. So there's this virtuous interaction between the two, which I find really exciting. The other thing I want to notice, if you look to the far left on the screen, is that the evolution of analytics is by the more and more moving away from the frequentist techniques, which are at sort of low-level descriptive and predictive, and much more into the Bayesian. And those who are into the Bayesian frequentist discussion, it's real interesting how the resurgence of Bayes in the last 20 years and the discussions of Bayes in a lot of the books on AI and the like have really shown that is one of the key thoughts behind the successes we're having. Okay, now let's talk about business. For businesses, and this is the money for most of us, the money is a narrow AI. And what's going on is really very much analogous to the first industrial revolution. I'm surely not the first one to say that, and we're seeing it all and the like, but it's really worth pointing out. It carries out mental tasks well enough to be often more efficient than humans, sometimes even better. And right now, and for a while, it has replaced workers to manage risk-managed routine tasks, things like issuing insurance policies. This is a great example. This is a company which automated that process fairly early. You can go online and their decision engine will decide based on what you input and what it finds online in the credit reports or whatever its database is, decide whether or not to actually issue you an insurance policy. It'll create binders, and there's no person in the loop. And because the people understand the risk of doing that compared to the benefits of having done it, that is, they get to sell a lot quickly because people just want to get online and buy an insurance policy. That taking that risk is outweighed. They can quantify the risk well enough to know that that's outweighed by the benefits of doing this. Issuing credit, it's amazing how good Amazon is at having machines that'll take sales without any people in the loop. And there's lots of other examples another example right now is we have fund management software and particularly people's for things like retirement funds and the like. there's AI that will rebalance your fund every day if you want it to. And I think that's mostly just rules engines. There's the other kind, which I think is more where the real future lies. Those are going to be a bunch of the things at the top. By the way, long distance truck driving, I think, is going to fall fairly quickly because that's a lot easier problem than driving things around the city. If it goes from one place to a highway to another, I think building an AI that does that and taking the risk of exhausted truck drivers out of the loop, that's another one that's going to happen. Now, on the other hand, to get back to the enhanced workers, the idea is that there are some things that, like reading medical images or code migration, where you really can't fully trust an AI to do it, but it can do enough of it to make the people who are doing this much more efficient. So the thing that reads medical images can come back and say, hey, look, I found these things, somebody should look at that. If you can use machine translation to do code migration to a point, making the coders that much more efficient. This is also even true for language translation. You wouldn't let Google translate a big text and then publish it, but you would use it to do a lot of the work so that it could be checked more quickly by the actual translators. The other place where machines have turned out to be very useful is in dealing with uncertainty. As from the thinking fast and thinking slow material, people aren't as good at thinking slow, which means really understanding the implications probabilistically of the evidence they see. That's why the Bayesian engines, and that's partially why AI is beginning to perform better than people's, because when there are calculations that involve interactions on certain things, people just aren't very good at that, and that's why we have Bayesian nets and Bayesian neural nets and the like. So first of all, here's a quote from just a few days ago from Fast Company. AI is going to kill 2.5 financial jobs and save $1 trillion. This is exactly like the Industrial Revolution, and we're going to see all the social displacement due to that. But let's talk about Aptage for a moment. This is where Aptage comes in. So what happens is, imagine you're a manager of a development organization at various levels. Either you're looking at the full P&L of the development function, or you're looking at meeting deadlines. What happens so you're owning this whole problem, but at the beginning you own this whole problem. You look at your organization trying to develop a new product, and in the early days often of these kind of efforts or of their teams, they go through a whole lot of churn. And one of the things that would be and so the question is there enough churn so the organization is learning, but not enough churn, but so much churn that they're not actually proceeding? So it'd be really good to have a measure of that. A person can't do that by seeing the data, but an AI engine that can learn from the arrival rates and the work-off rates and see how these things are converging, that would be a great example of how AI can be used. Now, once you actually have to a stage that you've gotten through past the churn and actually and functional, the first project you're starting is going to be very uncertain. It's the first time you've done it. You don't have complete information. The risk, so you can't make firm predictions. All you can do is make good enough predictions to know if you can move forward. And at the end of the project, though, you have to be absolutely certain that you're going to deliver, because tomorrow I'm going to deliver. I'm pretty certain of that. I wouldn't want to guess at that. So the uncertainty at the beginning of the project has to be much greater than the uncertainty at the end. And particularly if you're going to do interesting projects. And so rather than having work breakdown, what you really want to do is see how fast the risk is burning down. And that's another example where people aren't very good. The good project managers are really good at this, but most of the run-of-the-mill project managers are not. And this is a skill that AI can enhance and bring that intelligence to that level. Now, once a project is in place, either because if it's an internal back office thing or it's something in the market, there's all kinds of these days, risk of disruption. If it's an internal project, what's likely to happen is there'll be new automations, and the system you invested in a few years ago is no longer the most efficient thing, which makes your company less competitive. Or somebody's coming to the marketplace with some new concept and essentially disrupted your marketplace entirely. Now the question, there's a lot of, what you want to use is the right kind of market evidence, looking at that, and consensus experts' opinions or whatever to understand the question is, what is your timeline? Well, how probability is it you're going to be disrupted tomorrow? How probability is it going to be disrupted in 6 months? And understand as a function of time, when and how much disruption you're going to see. If you decide you are, then you have to start looking at alternatives and build risk-reward portfolios. And then having done that, looking at them more carefully with probabilistic J-curve to S-curve projections so that you can understand the total life value of your project, make the invention, make this investment, and goes quickly. But now you're in the risk burn down situation again. The good news is, because you can successfully know that you don't have the techniques to manage innovation and risk burn down, you're somewhat confident in making the investment and moving forward. And if you have a new team, you may be back at the churn days. If you're not in the new team, then you get to go around this cycle. And that's what Aptage does. I'm sorry. What Aptage does is provides tools for each of these things, for applying machine learning, Bayesian techniques, learning from the evidence as we go, not just from industry averages and sort of frequent samplings like some of the other things do, but learn from your project in all these cases, or learn from evidence that we get from the marketplace and whatever. Apply that learning to build out the probabilities to provide the good, at least prescriptive analytics in cases. So in the risk burn down, we recommend actions. In the portfolio stuff, we recommend the right investments. So I have some final thoughts. I really thank you all for staying with me. I will start taking questions. There are a few, I think. So first of all, and is that AI is not so much a big revolutionary new idea. It is just the evolution and convergence of several technologies. And the breakthroughs mostly came from computational neuroscience, but not entirely. But it's really the convergence of these things that have really worked. And here's a really important point. AI, as people, will always make mistakes. So the question, you can't build a perfect AI. We will never build a perfect self-driving car. So the question is, when is the AI good enough to deploy? Given that the AI will make mistakes. And right now, we have, culturally, that's a problem we're struggling with, more so. And by the way, driving better than people isn't that high a bar. For most of us, the money is in narrow AI. We really are having an industrial revolution. If you're thinking about using AI, you really have to ask yourself, just like adopting any other technology, what are the benefits I will get? What is the cost of doing that? And it's just like adopting, as I said, adopting manufacturing automation. Now you're adopting it for your white-collar workers. And in particular, and particularly given that the kinds of skills we need to do the kind of innovative work we're doing today, a very small percentage of the people out there really are deep enough to do the kinds of management that we're finding more and more people need. And that's but AI can help upskill the people. And finally, between AGI and conscious machines, sorry about the bulleting on this. AGI, we're going to see are having huge investments. This is the development centers at each of the Amazon and Google and Apple are putting up, they're having huge investments in AI. I don't know where they're going to get all the skills. They're going to they're putting in Boston a 2,000 person AI development lab. That's Amazon. That's not even their headquarters, just 2,000 people just to do that. And Apple and Microsoft have announced equally large investments. And then conscience machines will happen. It'll be really intriguing to see if it really does take quantum computers to do that, but it's going to, as I said, I expect to live to see it. And then finally, those of you who are interested in looking at AI for development organizations, we're here to help. Thank you. I include in this presentation, which we'll make available to people, some references that I think you'll find learning and sort of prove the points. And now, are there, John, do we have any questions?
Yes, thank you, Murray. We do have one question from Ricky, and I think that's Ricky Solomon.
I think it is too. Hi, Ricky.
The question is, how does Aptage apply to AI specifically as opposed to helping plain vanilla software development?
Well, what's happened in plain vanilla software development is they've been confused. The thing, one is there's no such thing as plain vanilla software development, Ricky. But where the trends have been is there's essentially two schools of thought these days. There's the software factory view, which is still around a lot, and then it gets reflected in the DevOps environment, which is really how those things flow through the development lifecycle from change requests or of some sort to deployment, and automating that as much as you can and making that as efficient as you can. And that's applying a lot of lean thinking. And then there's the agile community, which is looking at small cycles and breaking the work down into small enough pieces that you can pretty much sort of predict how long they're going to take. And then you manage the team to a steady velocity, and then you can make the development predictable. Experience has shown, one, that even with, in both cases, either the DevOps view where you start looking at lean things and you look at time things in state and manage the flow through that. That's best discussed in Reinertson's book on second generation product flow. What happens there is that the things are either in a backlog state or in a process state, and the time in state is actually remarkably uncertain and has some really interesting probability distributions. The current state of the art doesn't look at that very much. This kind of thing, Aptage can learn those rates and start anticipating sooner when you should take action and readjust the DevOps flow or the factory model flow. And this is exactly what Reinertson suggests people do. On the agile side, we've discovered two things. One is the idea that extending agile just a little bit from the standard planning poker, we don't know how big this is, but we can assign sort of Fibonacci's or shirt sizes to this and get people to agree. That's throwing away information, which Aptage can capture and do a better job at handling planning poker and even things between a 3 and an 8 point story. If there's some probability, it'll be a 3 point story, some probability it'll be a 5 point story, and some probability an 8 point story. We can capture that wisdom of the team rather than arguing about which one it is, which gives you information for now doing a more predictive model of what your velocities would be, what you should plan for. Second, what your velocities need to be. Second is we have found that, and this is that in almost very rarely do you see particularly a beginning team ever get anywhere near a state of constant velocity. And the velocity estimation tools out there really require a lot of machine learning. You can't do, if you do curve fitting, you're going to overfit the data. There's some ad hoc techniques out there which are dead wrong, but the Bayesian learning techniques at Aptage Brains actually gives you a really good probability distribution of what your velocity will be given the velocity in the past from remarkably small data sets, and helps you plan for being just aggressive enough in the next iteration. And then we can roll that all the way up to when you have big stories which haven't been yet decomposed, epics which haven't been decomposed into stories. We can help you work with, we can put those into, we can use predictions around those too. So you can do the good agile thing and not decompose everything at the beginning of the project in order to do the estimate. And we can, with the ranges around those, you can do the risk burn down even prior to story decompositions of epics. That was a lot. Thank you for that. I had an answer to that question.
So Jim Densmore has a question.
Yes.
Agile has attempted to avoid all the analytics. Don't consider uncertainty, just use Fibonacci. At the individual team level, maybe we don't need Aptage. Where is the line? When do we need AI? In parentheses, he states, maybe sales you've made already provided a crowdsourcing answer to this, question mark.
Well, so there's two parameters, Jim, for this. One is the community that has been the community that really dislikes the no estimates crowd, which you bring up, have had really bad experiences in the past by applying the wrong analytics, and we understand that. And so they're shy of anything right now. And their attempt, as you said, to do that is to just use the is to get a somewhat approximation of that using the Fibonacci sequences. But we have found in talking to the people who talk to us say, yeah, but on the other hand, there's a whole lot of people who say, we've tried Agile and it doesn't work. There are teams for which that works. The team is cohesive enough and they have been in process and mature enough that probably they don't need Aptage. New teams, teams that are missing their deadlines though, and are in the green, red phenomena, and still applying those techniques would really benefit a lot from Aptage. And we've seen, and yes, we're seeing that from working with our customers. We're also finding Aptage has a stronger adoption right now with big, complex hardware, software, co-development, IT projects, and product development, where there's now multiple teams. They have interactions between the two. They have dependencies between them and separate velocities at each team. And so they're working in parallel. They're not necessarily waterfall. We can do major iterative development and integration-driven development with these kind of projects, but there's still a lot of uncertainty about whether each team and the joint probabilities of everybody actually meeting the deadlines they're hoping to. We find out that's probably more of a sweet spot for Aptage than certainly than a DevOps team.
All right, and so Jim makes a comment. He said, okay, so even individual teams, cool, thanks. Multiple teams of, for sure. The notion of being able to well estimate features for an agile release train of 100 people resonates well with me.
Thank you, Jim. I'm seeing you here.
Okay.
Yeah.
So Cindy Van Epps asks, as an agile and scaled agile coach, I've evolved to not talking about estimating. It's about sizing and commitment. I can see where AI can offer options for an impediment the team is facing or reality check on what a team is about to commit to. But it should only be another voice on the team. Otherwise, the motivation and maturing of the team may be taken off the table. Thoughts?
Oh, thank you, Cindy. By the way, Cindy and I have known each other for longer than either of us will admit. And Cindy always has really good thoughts. So let me address them. One is estimation versus sizing and commitment. In my mind, I'm using them interchangeably. I understand others don't, but it's really hard to get the terminology right that everybody hears the same thing. So your way of expressing it, which is we want to get a range of, we want to treat sizing as a probability distribution. And that dates back to Pareto methods. and then make commitments based on rolling up those sizings in an appropriate way, which is, again, applied probability. It's exactly what we're trying to do. What was the second question? I'm sorry. John, there was two questions there.
Yeah, so
Maybe hold on.
it's facing a reality check, right?
Oh, yes, that's the other point. Thank you. That was all I needed. That's exactly my point. Cindy, I completely agree. You don't want this. I don't think this is good enough to be autonomous. I think it's a member of the team, just like you said. It enhances people's skills, but doesn't replace the people. That's really important. And so what happens, what we have found is that people have sort of gut feelings, but they don't really know. When the thing gets complex enough, a team may have some gut feelings, but they don't really know. And they're uncomfortable. So if we can show them a dispassionate, I wouldn't use the word objective exactly because there's subjective things in there, but a dispassionate machine that captures their best beliefs and the evidence at hand and tells them its implications. And they look at that and say, oh, then I'm going to change something. And because I didn't realize the implication of that assumption. And so it becomes part of the team. It upskills the team, but it doesn't replace the team.
Yeah, and so Jim Densmore also made a comment about, I think second to last slide when you're talking about good enough.
Mm-hmm.
He states, not sure a question yet, but on your last slide, another model for good enough is airline flying. Airline pilots and their high level of capability, the public asks for, and the result is you're safer in the airline than in your bed, possibly a worthy discussion from which we might both. And I think that's where it stops.
Yeah, okay. Jim, absolutely. It's a really good example. And, you know, and as you well know, most of the time, so there's two thoughts here. One is that actually driving a car is harder, other than taking off and landing, driving a car is actually harder than flying an airplane. And you and I could talk about that over whiskey sometime, but seriously, there's a lot more decisions and sensors to be made. If an airplane is flying itself, at least a modern, highly aerodynamic, well-engineered airplane, it just flies itself. Now, on the other hand, often airplanes land themselves as well, most of the time, but we're not willing to let there not be a pilot in the cockpit at this point. We can't imagine autonomous airplanes carrying passengers, even in these days of drones. Now, will be a real interesting study to talk about this is to really look at the safety of drones in sense of their self-preservation and compare that to whether the pilot is making enough of a difference to pay all these pilots to fly around all the time, because they're very expensive. I'm sure airlines have a economic incentive to get rid of the pilots. And so the cultural question is, when are we going to trust that technology? Or maybe we would have someone just monitoring 100 commercial airplanes from the ground. So these are the kind of automation questions that have faced business forever. And these are really good examples of where we have aircraft industry is probably a really good examples of where we've done a lot of that and invested a lot in the science so at least right now, as you said, the evidence is very clear. The safest, if you have to choose between going outside and taking a walk and taking an airplane ride, you're probably better off on the airplane.
Yeah, so Jim's comments, harder tactically, not necessarily strategically.
Yeah.
And also another comment, drones are crashing all the time right now.
Okay, well then we know. It's a good test.
Yeah.
I was curious, actually. I had no idea. So
yeah,
let's not have autonomous airliners yet.
All right. So another question, can you talk more about the data needed by AI systems? How much is required?
So there's two Yeah, this is a really interesting question. A lot of what you hear about is big data, and that's a lot of what modern AI systems do are essentially classifiers, and they classify populations of things into categories. And if you're trying to do that kind of learning, you're going to need big data to do that. Okay. But there's other kinds of AI. So let's take it. So a really interesting example. There's always two things. One is, if you're going to classify big populations into things, then you're going to need large population data to do that. Often AI problems involve small data sets, and they just do. So one of the things that's really facing predictive medicine or precision medicine is if you treat it as sort of a large data calculation classification problem, you find that the number of people that have this measurement and this symptom and this genetics and this biomics and whatever, you start out with 100,000 people and you're down to 10 by the time of interest. So that's not going to work. So what people are doing instead is this is one of the reasons, I think this is really one of the key reasons why Bayes is so important right now, is they look at populations which are they look at just smaller sets of intersections, and then they create the marginal probabilities for those, and then they use Bayes' theorem to sort of project what is the likelihood of, say, a treatment working based on applying Bayes' theorem several times. And you're seeing that showing up in the marketplace. Other people are doing the same kind of thing using Bayesian neural nets to a point that they are remarkably good predictions. Now, they don't need, at this point, you won't have big data, but you'll have enough data to create the probabilistic models to do better than you're doing today. And then there are some cases where you even have smaller data sets. And in this case, what you do is you use some innate domain knowledge, and you understand where the parameters are. And you do a parameter learning algorithm, again, starting out with very general assumptions about the shape of the distributions of the parameters in the distributions, and use a Bayesian learning for figuring out how to update those based on the experience. Now, those tend not to overfit the data and do a lot better job than other kinds of algorithms. So the answer to the question is how much data you need, and the answer is the standard consultant's answer, which it depends on the problem.
All right. I think
these are great questions.
And I think
thank you all.
We're out of questions now.
We are, and that's good. So this is our first time through it. We have a quorum. I'm really pleased to see that. We're going to learn from, we are always learning. We're going to learn from the questions and the comments. Thank you all, and look forward to hearing from you. We're going to put this presentation on the web, and I look forward to hearing from you with more for comments and questions and whatever.